Okay, welcome back everyone to day 2 of our little workshop here. It's my pleasure to introduce our second invited speaker, Samaey, professor from KU Leuven, who's going to give our first talk today. Just one announcement before I hand over to him for his planned YouTube video. For the group photos that we are going to have later, because the weather is like not too nice looking, please everyone collect at the staircase. We're going to stand up there and Mira is going to take the photo from downstairs. Say it again after the second talk in the morning because we have the photo at 11:45. Okay? Then please join us. Take it away.
Thank you. So thanks for the invitation. And for showing up for the first talk in the morning. So I'm going to talk about multilevel Markov chain and interacting particle methods for Bayesian inverse problems. And you see the word "and" in the title, which means that there is going to be 2 parts. The first part, multilevel Markov chain, Monte Carlo methods for Bayesian inverse problems. And then the second part, on interacting particle methods for the same problem. This is going to be the setup of the talk. This is the first part, and basically this first part is the PhD of Pieter van Mechelen, who I co-supervised with Geert Lombard. Geert Lombard is a professor in civil engineering, structural mechanics at KU Leuven, and they have issues in inferring parameters of built structures. So the structure that they have monitoring is something like a bridge, which, because we are applied mathematicians, we represent as a square rectangle, a rectangle. And so that's supposed to be the bridge, but for the algorithm development that doesn't matter. The issue that they have is that if you want to do a finite element simulation of this bridge under load, this is a high resolution finite element simulation, so expensive for just one simulation. If you want to infer the parameters, the stiffness parameter of the bridge, which determines how resistant it is to deformation, this is, for the inference you need to run the simulation multiple times, many times. So each simulation is already expensive. That's problem number 1, a high resolution model. But I'm struggling because of the fact that I want to use the pointer, but I don't have the pointer. High resolution model. The parameter that we want to estimate is a function of space. So in principle, it's an infinite dimensional parameter. The stiffness is a function of space. So this is what we call local parameter estimation. It also adds to the dimensionality of the problem. And the specific situation that these civil engineers are in is that they want to use high resolution data. They want to use, like, they have these strips that they put on the lower end of the bridge, and they have, in this one line, they have displacement data as a function of the coordinate on that one line. So that's a function as data. It's not really a function. It's many data points, but you can consider it in the limit as being continuous data on the line. Or they have a movie of the bridge vibrating. And so they have full field data, not really full fields. They have high resolution pixelated data. But in the limit we will consider this as full field. Why? Because we are going to try to see if we do multi-level Monte Carlo or multi-level interacting particles, we want to change the resolution of the grid with which we simulate the finite element simulation. And it makes sense to then also change the resolution at which we look at the data, as you will see later on. And to do that, we will consider the data to be discretizations of available full field data. That's basically the setup. But for the proofs, we will consider that sometimes we will consider full field data, and if we don't manage, we will consider to be high resolution finite dimensional data if we don't manage to prove in the full field setting. So that's the setting. So the issue here, multilevel Monte Carlo methods exist, and you've seen a talk yesterday already about them. But the added thing here is going to be the fact that we want to have high resolution data and also locality. So this is the setup of the problem, as you've seen already in other talks. So there's a finite element model. It takes as input. I do have it. It takes as input a stiffness parameter that we want to estimate. So that's the parameter in the model is what we want to estimate. If we would have it, we would simulate the model and obtain the model output, and we will compare the model output y with observations, and the difference will be attributed to measurement noise. We will not consider the difference to be attributed to model error, but it can also be model error, but we will assume that it's measurement noise. Okay, so that's the setting. So Bayes' rules then tells you that you can obtain a posterior distribution of the parameter given some measurement y as, so this is the likelihood, so this is the probability or the likelihood that the data was generated by the parameter. This is basically a measure for how well the parameter can explain the data. That's how people often say this as well. There is some prior distribution assumed on the model parameters. There are two ways of assuming a prior. Usually, if you don't know anything about the problem at hand, you put something very wide as your prior, and then you say the data will have to narrow it down. Or in the situation that we are here, we often have also, the bridge was already built, so we have some prior information about what the bridge is supposed to be. And then the inference problem becomes, did the bridge change, basically? And this is somewhat more tricky, because if your prior distribution somehow doesn't capture the changed bridge, you might not find it. So this is a bit tricky. But and then the evidence is just the probability of observing some data, which is something that you typically don't have and wish to avoid to evaluate. So we will try to work only with the numerator of this fraction, and that's why we will use sampling methods. Of course, you can try to optimize the posterior distribution so that you find the most likely parameter. But my belief is that without at least doing some uncertainty quantification, or to at least have some idea of what this posterior distribution looks like, this is not very informative, because you will always find an optimal or a most likely parameter, even in the case where you don't have a lot of data. And so to know if your optimum makes any sense, I think you need to know a little bit more about the posterior distribution. And what we then like to do is say, okay, we need to know at least a little bit more. What if we want to know the whole posterior distribution and we want to sample from it? That's the setting that we are here. It's not really always necessary to have the full posterior distribution, but at least it's an interesting problem to think of computationally. We might want to have some moments of this distribution, like the variance, the mean, etc. Okay, so the problem here is linear elasticity. So those are the equations. There is a Young's modulus, E, and there's a Poisson ratio, I think, nu, and they, oh, wrong button. And we want to find the posterior of the Young's modulus given the model that we have and some measurement data. And what we will assume is that the measurement data is either full field in this situation, which means we consider the bridge to be 2D and to have taken a photo, or we consider line data on the boundary, which is equivalent to the setting that I said about having the sensor, a line sensor on the edge of the domain. Those are the two settings we will consider. The random field we will model via a Karhunen-Loève expansion, but there is an issue with this KL expansion because the bridge has a maximal stiffness, so we can't simply assume a log normal field. We have to assume a field that is bounded also from above. And so we do this gamma distribution. So we take AKL expansion here of a normally distributed random field, and then we plug it into this transformation that you see here to get the gamma distributed random field. And so what we will do with multilevel Markov chain Monte Carlo, we will prove that the convergence rates also hold for such and different distribution, not only for log normal distributions. This is Markov chain Monte Carlo in a nutshell. I suppose you've seen this yesterday already too. So you take an initial state, you generate a proposal, based on the likelihood and the prior, you accept or reject the proposal. When you accept it, you just add it to the chain. When you reject it, you add your previous sample again to the chain, and then you run until you think you're satisfied. That's important to say, until you think you're satisfied, because usually you can't know if your chain is long enough, so you'd have to somehow estimate stability of your estimated quantities over the length of the chain. And this can be problematic if you have some metastable behavior, and you haven't seen somewhere else. But this is not going to be the subject of the talk. In multilevel Markov chain Monte Carlo, which you've also already seen yesterday, so there is an issue with direct Monte Carlo at the finest level, and that is if you now suppose, so we have a finite element discretization. This gives us the cost per sample. And then you have the length of the chain. This gives you the number of samples that you need. The Markov chain Monte Carlo method is unbiased, so this means that the length of the chain somehow only determines the variance that you have, where the cost of one sample determines the bias that you will have on your estimates. If you want to reduce the total error, you will want to reduce both the bias and the variance, which means that you need to take longer chains with more samples per chain. That's the thing we want to avoid with multilevel Monte Carlo, and we do this in the following way. We basically write our expectation that we want, which is the quantity of interest at the finest level. The finest level is capital L, so the higher L, the higher the number of degrees of freedom. That's how you should see it. And we say we're going to approximate on a very coarse mesh. Of course, this expectation at this very coarse mesh will not be the same as this expectation on the very fine mesh, but what we will add is we'll add a telescoping sum. So what you see is Q0 disappears with Q0 here. Q1 will disappear with Q2 will disappear with Q1, etc. So the only thing that will remain in this telescoping sum is the finest quantity of interest. So this has estimates the same quantity, same expectation. The variance, however, is now governed by the variance on this level, and this is cheaper, so you can take many more samples, so lower variance at the same cost at this level, plus the sum of all these variances that you see here, but these are differences. So if you can make sure that these are correlated, and typically how you correlate them is because you take the same random sample of your random variable on which you evaluate, but you discretize it on two different meshes, you will get similar noise on both levels. If you subtract, most of that noise will be disappearing, and that's how you basically can estimate these difference estimators with fewer samples than you would need for the direct estimation at this finest level. And if the rate of decay of this variance is quick enough compared to the growth of the cost, you can get a cost of this multilevel Monte Carlo algorithm that scales with 1 over the tolerance squared, which is what you would have if you would be able to exactly evaluate your fine model, and you don't have to worry about the discretization. But of course you need a much more complicated algorithm to do that. Okay, so that's the situation here, but I didn't say yet what the levels are in our setting. And in our setting, the levels are coarsening in two ways. First way, this I have already told, is that the model resolution increases as a function of the level. So finite level means a finite discretization of the finite element problem. But the second thing is also that the parameter level, so the level at which we truncate the Karhunen-Loève expansion, the KL expansion, we also make that increase as a function of level. Why? Because it doesn't make sense to the scale terms, they increase in frequency. And so lower KL terms are smoother functions than higher KL terms, so it doesn't make sense to keep the more oscillating basis functions on meshes on which you can't represent them accurately. So you basically add basis functions onto the basis functions of the coarse level to go to the fine level. And that's actually what we're going to exploit, the fact that this happens in the multi-level algorithm. So those are the two things. But so this is basically how it works. You basically first generate a Markov chain at the coarsest level, the classical Markov chain Monte Carlo. And then you go to the next level, which means we refine the mesh. So all the samples that we have, we can refine the mesh and compute them again on the finer mesh. But we want to do this for fewer samples. How are we going to do this for fewer samples? We're basically going to subsample. So we're going to take every other, I was going to say, every other would mean a subsampling factor of 2. Every now and then we're going to take a sample, and the every now and then is determined by the subsampling rate. So in this case, the subsampling rate is 3. We take 1 out of 3 samples in this graph. Once you are at the fine level, we keep the coarse coefficients that we already had. That's what will make this sample correlated with that sample. The fact that they have the same first so many terms in the KL expansion. And then we just add a few extra terms in the KL expansion and we need to move forward. So moving forward means that we just stay on the coarse coefficients that we have received from the level above, and we sample new fine coefficients with precondition Krag-Nicholson, which is a typical proposal move that you can make. I'm not going to explain in detail what precondition Krag-Nicholson is. I'm just going to say that it's proven that this is somehow dimension independent, that the acceptance rate doesn't really depend on the dimensionality of the parameter. Which is useful in a context where we want to go to infinite dimension. Joseph?
Are you using the precondition Krag-Nicholson also on the coarse level, or?
Yeah, I didn't specify what happened on the coarse level, but yeah, indeed.
Okay.
Or you can do just a Brownian motion. We tested a number of things. I don't remember what turned out best, but you can. And so that's how the algorithm then continues. But now, multi-level Markov chain Monte Carlo was developed in situations, typically groundwater flow and stuff. You have a few places where you drill and you have measurements, but not a lot compared to the resolution of the mesh. Whereas here, we have full field data somehow, and we, if you would now, so if you would refine your mesh, in a typical situation where you only have a few measurement points, if you refine your mesh, you don't at the same time get extra measurements at your disposal just by refining the mesh. But here in our situation, because we have this full field data, we do have extra data points when we refine the mesh. And what we want to do is in fact the opposite. We have this data available, but on the coarse mesh, we want to reduce the amount of data in which the amount of points in which we want to evaluate the likelihood. Because on this coarser mesh, if you would want to evaluate your likelihood in all the data points, you would need to interpolate on the coarser mesh just to be able to evaluate your likelihood. So you would basically throw away a lot of the advantage of going to the coarser mesh. And you can actually see this in this graph. So the red line is multi-level Monte Carlo. So the black line is, of course, this is the cost of a sample at the finest level, capital L5. So of course, this is the baseline. So the cost reduction by going to coarser levels is visible in the beginning here because of the fact that you have you don't need to solve the finite element model. But as soon as the finite element model becomes so coarse, that's not the dominant cost anymore of evaluating the likelihood. The dominant cost is just evaluating the solution of your finite element model in all of your data points. So if you want to avoid that, you need to avoid evaluating your data in all your mesh points. So if you do that, then you can really get this linear decaying cost that you would have, and that's the thing that we want to avoid. So what's the issue now? The issue that we had was that we needed to change the likelihood function to go from the finer to the coarser mesh because the noise model basically changes if you go to a different level. I can explain this very intuitively as follows. If you look at this data point, it somehow represents information from around here. And if you want to have the likelihood consistent across levels, you need to make sure that the spatial resolution of where you measure your data is included. And this is done by basically considering this data point not as one of the data points of here, but as a projection of the data of all the neighboring points onto that point. Which means that you have to consider this data point as some sort of average of the data surrounding it. So there is a projection step involved, which reduces the noise if you go from a finer level to a coarser level. The perceived noise level at the coarser level is lower because it's considered as an average. But that again doesn't solve the issue, because if you have to do that, you have to compute averages over your surrounding data points, which again has a cost proportional to the number of data points at the finest level. Luckily, if you just take one data point from the previous level and you adjust the noise level in the likelihood, this is a projection operator that matches with what we need in the proof for assumptions. So the only thing we need to do is adjust the noise level, and we can just take a subset of the data points. And this works nicely, as you can see on the graph. So that's the first contribution that Peter made in his thesis. Second is, this is more a technical thing, because the proof that he started from was for log normal distributions. He thought it would be good to make the proof agnostic to what kind of distribution was involved. And I already told this, this log normal is not realistic for structural mechanics applications because you don't have a maximum. And now we can do that. So I'm going to briefly skip over that. Then the next problem that we face, and this is something that is still open for debate because so the proof of convergence of multi-level Markov chain Monte Carlo relies on a crucial step, namely that what comes from the coarse level, the dark blobs here, are independent samples for the coarser level. And the stuff that you add now is a Markov chain for the finer level, but conditioned upon these independent samples that come from above. That's how the strict theoretical convergence proof works. In practice, you don't have this, of course, because these coarse modes also come from the Markov chain. So how this is typically then solved in practice is by saying, look, there is decorrelation as a function of time. This is, you can measure this by computing the integrated autocorrelation time of your Markov chain. And if you just wait long enough, the samples are essentially independent. They are not independent, but they are indistinguishable from being independent. And then numerically, you would have to see the same behavior. What we have observed in our situations is that there are two ways to determine the number of samples that you need at each level. The first is from Markov chain Monte Carlo theory, or multi-level Monte Carlo theory, I have to say. The variance decay determines how many samples you need at each level. So if your variance decays with a certain rate, this gives you a factor with which you can decrease the number of samples per subsequent level. So that means that if you know what your bias needs to be, you know what your finest level is. And you can then, based on the finest level, you have some error there. You know how many samples you need at the finest level, you need how many samples you would need at the coarser levels, because just by multiplying with this factor. Okay? If you do that, you notice that you get a certain number of coarse samples that you need. And if we then look at the subsampling rate, the subsampling rate is what tells us how many samples we need at the coarse level for one sample at the fine level. So one way to know how many samples we need at the coarsest level is by just saying factor 2 or factor 4 all the way up. The other is the subsampling rate, which is typically much, much larger. So this means that although the coarse samples are cheap, we need to generate many more samples of this coarse level just for the subsampling that we don't need for the coarse level estimate. And this is, of course, annoying. So what we want to do is we want to reduce the subsampling rate while still having some guarantees that the method gives us accurate results. And what we'll notice, this is now just cost. If you look at the subsampling rate, you would expect the cost to increase monotonically as a function of subsampling rate, cost for a given accuracy. That's not completely the case, because with low subsampling rates, some non-trivial things happen with the acceptance rates in the chain, which make that for a given tolerance, you can have slightly shorter change with some higher subsampling. But as soon as you pass that, your subsampling rate really increases. But the integrated autocorrelation time is here, so that should be your theoretical subsampling rate. And you see that for a given accuracy, for a given tolerance that we put on our estimates, we could take much, much lower subsampling rates and still get away with that. But this is just an observation. The question is why? So what did we do? Heuristically, we say that we first do burn-in, and then after the burn-in, what we do is that we just say what are the numbers of samples that we need at each level for the convergence of multi-level Monte Carlo. And we take the subsampling rate such that this matches. This is computationally most efficient, because if you take a higher subsampling rate, then you have too long coarser chains. If you take a too low subsampling rate, you need to add samples at the coarsest level just to have enough samples at the coarsest level. So this also comes with an extra cost. And you throw away samples in between. So that's how we're going to do this. And if you look at that, what this does is that if you would do the classical rate, these are the numbers of samples that you would need on the first 3 levels. And this is what our proposed rate gives you as number of samples. So it's a factor 10 reduction in computational cost. So it is worthwhile to do this if it's allowed. Yeah, Elisa.
Quick question. Do you need to decide the level that you stop in advance? Or you need to decide which level you want to stop?
Yeah, in this method you have to, because at the finest, you need to know how many samples at the finest level, and from there you build on what coarser levels you can do. And
do you have an estimate or somehow to estimate how many levels you want? Or you just based on the samples that you need?
So basically, at the finest level, we use the discretization error. That's what determines what the finest level is. And then for coarser levels, we just do some kind of factor 2 always. So that's the typical thing we do. And now, speedup is one thing, bias is something else. And we have been discussing, so Peter has a proof that shows that even with subsampling, the Markov chain gives a detailed balance, which means that your Markov chain should be unbiased. However, what we see is something else, namely that if you decrease your subsampling rate, the first corrector term, the expected value of the first corrector term is different for lower subsampling rates. So that's the problem that we are still stuck with. We have a proof for detailed balance. We don't find the error in the proof. I didn't say there is no error in the proof. I say we don't find the error in the proof. However, we've looked for quite some time. But we do see this increase or this difference in the first corrector term. What we think it is that if you have a lower subsampling rate, your coarser chains are shorter. So this means that they cover, so Markov chain Monte Carlo typically says that the integral over an infinite time horizon is the expected value that you're looking for. But here we are looking for an integral over a finite time horizon. And we say this has to be a good approximation of infinity because we can't do any more. That's basically the gist of the argument. We have to stop somewhere. With lower subsampling rates, we stop sooner. With higher subsampling rates. Let's see, what is a subsampling rate? If the coarser chain is shorter, so if we use more coarse samples to go to the fine level, then your coarse chain is shorter, which means it covers a shorter time interval. And what we are testing now is if we increase the time interval, so if we increase the total length of the chain, how this error decays. But this is very difficult because the noise also decays then, and it's very difficult to distinguish noise from bias. So what we think is that this is a finite chain length artifact, and not a proof that the method is biased. take it for what you want, and people on YouTube can also think of it what they want, and maybe in a year we will know what this is. Okay. Next thing. We have said at the beginning we are going to do Karhunen-Loève representation of the stiffness parameter. This is something that always passes if you say this without thought, because everybody does it. In this situation, I've shown you the image of the bridge. We are looking for localized damage. That's basically the thing we are interested in. KL expansions may not be the best way to represent localized damage because they are global basis functions. So we were wondering, what can we do if we look into different parameter representations for this problem than a KL expansion? Also, each of these terms doesn't give us a clear physical interpretation of what the underlying coefficient is. So we looked into 3 different parameter representations. One was the KL expansion. The second one is a wavelet-based representation. And you see here one of these basis functions. Where is my mouse? So it contains some localization. So you know what wavelets are. So they are oscillating functions. You have the scale at which they oscillate that you can vary, and you have the location that you can vary. So you have more basis functions required for the same frequency and locality than with KL expansions. But at least you can localize, because if only coefficients with localization at that place show up, then you know something is happening in that space and not elsewhere. But this is not really a basis; it's a frame. So it's a redundant representation. So we need to take care of that as well. The third thing is local average subdivision, which is basically saying, let's take the stiffness value in each of the grid cells, and if we go to a finer mesh, we just have to take the average and the differences, and then we build a hierarchy like that. So this is truly local. What is now the difference between these 3 parameter estimations to solve the inference problem that we want to solve? Well, it's difficult to look into this in detail. The first thing you need to worry about is if you represent your functions in such a 3 different bases, you need to make sure that your prior distribution on the coefficients of these basis functions represents the same prior distribution. That's one big issue. The drawback of this is, of course, that you need many coefficients. You need one coefficient per grid cell on each resolution level, whereas with KL, this is independent of the mesh size resolution, the number of terms that you take. So on the one hand, this is advantageous because with KL you need to think on how many terms you need at each level. Here you don't, but you get more coefficients at the final level than you would with a KL expansion. KL terms are optimal because they contain the maximum amount of information in a given number of basis functions. But there is a PhD thesis that we found in 2011 in which it says how you can define probability distributions on the coefficients of such basis functions to give you the same priors as you would have with the KL expansion. This is a thesis that Peter found, hardly cited, but very interesting thesis. And so what we are doing now, that's not in preparation, it has returned because we submitted it to our own journal. What you see is if you estimate the posterior mean after doing the multi-level Markov chain Monte Carlo in each of these 3 bases, you get different posterior means, but similar accuracy, I would say. The thing you see here is that with LAS, you do get this localization a bit more than with the others, but I wouldn't say it's dramatically different. The question is, what about cost? And standard deviation also reasonably similar, slightly more localized for local average subdivision. The interesting part is here, the computational cost. Because you would expect that because local average subdivision has many more, a very high dimensional representation of the same parameter, it will be more costly, but it isn't. We see the same convergence rates as a function of error for the three methods. This is just the standard Markov chain Monte Carlo rates, but we see a lower constant for lower average subdivision. And part of the explanation has to do with the acceptance rates. With local average subdivision, we see that, so this is 1 minus the acceptance rate, so this is the rejection rate. The rejection rate at lower levels is much lower for local average subdivision. So with this parameter representation, we get a better mixing chain, basically. And so we get, so that's where the efficiency comes from. Okay. So what we have here now is the conclusions of the first part of the presentation. Multilevel Markov chain Monte Carlo with resolution-dependent data, some analysis for more general random fields, a heuristic for more efficient subsampling. You see the band-aid icon there. We think it's more than a heuristic, but we can't tell more at this moment than it is a heuristic. And then a comparison of parameter representations for localized damage assessment. With this different parameter representation, with local average subdivision as being superior in this context. And now I want to talk about interacting particle methods for the same problem. Why? Because of the fact that this is already what Elisa hinted at with her question. We somehow need to know, before we start, already the length of the chain that we want, somehow. It's decided by the number of fine samples that we need, or the we need to basically first decide what the finest level is, and then we need to base our chain lengths on the accuracy that we want for the variance, and then this sort of determines how long everything needs to be. If we want to then increase accuracy. With multilevel interacting particle methods, we hope that we can be a little bit more flexible. Also, the other disadvantage of Markov chain Monte Carlo is that it's inherently sequential, because you have one long chain that you're building. So if you would be able to do parameter likelihood evaluations in parallel, this could speed up things in terms of overclock time, because you can use multiple processes at the same time. If you then do that and you want to make sure that the fact that you do this simultaneously helps you, you need some kind of interaction between these particles. So the idea is then to develop artificial dynamics for an ensemble of particles, such that at population level, the ensemble of particles evolves from the prior to the posterior somehow. That's going to be the goal of this type of method. So this is no longer Markov chain Monte Carlo sampling. This is dynamic evolution from a prior to a posterior distribution through artificial dynamics that is driven by the data. Okay? So there are three components in such dynamics. You need to do a likelihood evaluation. This will give you a gradient that will tell you which direction each particle will want to go. Then you need some kind of interaction between the particles that tells particles, and this depends a little bit on whether you want to optimize. If you want to find the maximum a posteriori, you somehow need all particles to converge onto the same, let's say, global optimum, or guess of the global optimum. And the way that you do that is that particles basically contact each other and say, look where I am, this is better, come here. Or if you want to sample, this is the opposite, you want to explore the whole phase space. Basically what you want to do then is that particles avoid each other so that they sample phase space. And then particles say, I'm already here, it's good here, but you search somewhere else, maybe you find something better. And this is the way that they interact with each other. And then there is some randomness to ensure that you don't lock into whatever local state you are currently, just to make sure that you keep exploring. There are many example dynamics that you can think of. McCain-Vlasov equations are typically used for this. Ensemble Kamal sampling is a thing that I will talk about. There's consensus-based sampling. Elisa knows a lot about consensus-based sampling, I guess. And there are many methods based on kinetic equations, and because they are not so known, I put a reference to a paper on that on the slide. The idea is to look into the posterior distribution as a potential energy. So as I said before, we have a forward model, takes parameters as input, add some noise, this gives you your data. Your posterior distribution is proportional to likelihood times prior. If your likelihood would be an exponential distribution, a normal distribution, so that means that you have normally distributed noise with mean 0, and your prior is also normally distributed, then you basically get just, you can write your prior as the exponential of minus some potential, quadratic potential, that you can sample from. This is classical. In ensemble Kalman filters, so ensemble Kalman sampling methods, I have to explain a little bit. Who knows what ensemble Kalman filtering is? Okay. So that's clear. So you have a state. So for those on YouTube, most people here raise their hands. So you have a state. The model tells you how the state will evolve to the next state. And then you have an observation. State gets observed. That's your data then. And there is some noise in the observation. And what you basically have is you only have the observations and you want to reconstruct the state. That's how an ensemble Kalman filter works. And that's the formula. So basically what you have here is you have the difference between your real data and what you expect to be the data based on your model prediction. And then this is basically your noise, which is the difference between what you expect and what you actually measure. That's your noise. And what you see here are two is a covariance matrix. So basically what you do is you somehow here weigh how well you trust the model. That's this the covariance. So this is if you expect this to be large, it means that you don't trust your model a lot because you expect already a large difference between your model and your prediction. And the noise covariance you know because you know your measurement device, and so you basically weigh how much you trust the model versus how much you trust your data. And that's how ensemble Kalman filtering works. You see everything here is linear. Ensemble Kalman inversion basically says we have a dynamic model, but let's include the parameters as state variables, and let's say that we know that the dynamic evolution of the parameter is 0. This is just a trick, eh? Parameters are state variables that don't evolve. And that's how Kalman inversion works. Kalman sampling is then adding stuff. So let's see example Kalman inversion. This is now your extended state, and this is basically showing if you have this quadratic potential, this that I showed you before, which is your which represents your posterior. You find the maximum a posterior with ensemble Kalman inversion. If you do this, you have to now compare this ensemble Kalman inversion formula with this one. You see a few differences. First, there is a time step. That's not really that important. It's because here this is just in discrete time. But here we want to be able to take the time going to 0 to have a time continuous limit of this process. But you see this error of your forward model. You see your noise, which is here. And you see some extra. That's the problem with the pointer. I have two monitors. And here you have an extra term that somehow determines the fact that you want to keep on adding noise. So, no. Yeah, I'm not going to be able to explain this in full detail in a minute. But here you keep sampling. So these samples, well, after some time, they sample from the posterior distribution. So this is ensemble Kalman inversion plus extra noise to ensure that you sample. How do you want to make that multi-level? So we have now our multi-level Markov, our multi-level Monte Carlo trick that we want to use. How are we going to use that for such interacting particle methods? But the trick is simple. We are going to consider sets of particles that live at different levels of resolution. What changes with the level of resolution? The only thing that changes is the evaluation of the forward model that is now done in different resolution levels. That's the only thing that differs between different levels of resolution. If you want to make the coarse and the fine particles correlated, they need to be evaluating for the same parameter guess, and they need to take the same noise in the evolution. That's what's happening here. But the question is, what do we do with the interaction term? The interaction term that determines the covariance structure of your ensemble of particles. That is what we're going to estimate in the multi-level. So we basically take this green term, which is the covariance of all of these differences. We're going to estimate that in the multi-level way with this method. We can do some convergence analysis. I don't have time for this. And I can show on a toy example, which is, in this case, it is a Darcy flow with fixed data. And what you see is that for ensemble common inversion and for ensemble common sampling, you see that the rate, so this is accuracy, root mean square error as a function of cost. The rate at which the root mean square error decreases as a function of cost is higher for the multi-level than for the single-level Monte Carlo. But if you have relatively low cost per sample, you don't win. You only win if the problem is expensive enough for this method to pay off. Because of the fact that if you don't need if you don't need the accuracy, you don't need the final limit, etc. Okay. But the Markov chain Monte Carlo method had one big advantage in that we could choose the number of the parameter discretization at each level independently. We had more KL terms at final level and at coarser levels, and everything that I have told here, the fine level and the coarse level parameters are the same. The only thing that changed was the evaluation of the forward model, not how many parameters or the parameter discretization. That didn't change. If you look into this situation, now the notation has changed, unfortunately. You have to think about this as being, and the reason is because otherwise I couldn't get this on one side. But this is the update of the parameters based on the current guess and on some random. And then this is now, and theta is the interaction term now. So theta was the parameter in the previous slide, it's now the interaction term. And what was theta on the previous slide was the parameter, this is now u. So I apologize for that, it's because it comes from a different presentation. So the question is this interaction term, if it's multi-level, if it's multi-levelly estimated, we would need to have the parameters in the same space, so meaning the same number of parameters at each level. We don't want that. We want to have different parameter discretization at different levels. So the question then is, these difference estimators, how are we going to estimate them? And the solution, so that's the question. We have these difference estimators, but the parameters at the fine level and at the coarse level live in different spaces. We can't directly subtract them because these don't have the same dimension. So we need some kind of projection between the two levels. And the question is, what properties does this projection need to satisfy? And so then Toon, who is one of the PhD students in the group, Toon likes to take abstraction to the extreme. And what he said was that, look, if we have the following, the parameters actually live in a Hilbert space. It's a continuous parameter, the parameter is a function. If you then restrict your parameters to a finite dimensional subspace of the Hilbert space, and afterwards you discretize into an ensemble, or if you first discretize into an ensemble, but each parameter in the ensemble is a function, and then you project onto a finite dimensional subspace, it should be the same. So this gives you a projection operator. So this is now, so all parameters in the estimates now live, so rho maps you now from a finite dimensional parameter space to the function ensemble, and then phi maps you back to, so basically what he does is he pads, and that's not the key thing. He says, let's pad such that all parameters live in the full function space after padding. So you can do this with either adding zeros or by sampling from the priors, anything you can do. Anything that brings you from the finite dimensional space to the full Hilbert space, then you do all your computations, the full Hilbert space, and you project back to the level that you need. And then he came into this issue, because this is also something we haven't discussed yet. We are doing now as if we can, we just need to pick a parameter, we have some data, we find the posterior distribution of the data given the parameter. And he has done this with his multi-level algorithm now with level-dependent parameters. And what he has done here is a very artificial problem. He's taken a KL expansion of the permeability coefficient in a Darcy flow problem. And he has put the ground truth to the red dots. All odd terms have coefficient +5, all even terms have coefficient -5. Why? Because it gives a nice graph. And the nice graph that he gets is, what do we actually learn from the posterior distribution afterwards? And what he sees is the following. The first few modes you learn from the data. But the remaining modes, we don't really learn because the priors were standard normally distributed. So what does this mean? That everything that I'm telling you now is how we can estimate high-dimensional parameters, high-dimensional functions from rich data using high-resolution finite element models, so very expensive computations. And we can get these posterior distributions efficiently. That's what I've told you so far. The posterior distributions that we get seem to be the prior for anything except for the first few KL modes. So the question then is, why are we doing this? Why shouldn't we just, with a very coarse resolution model, simply estimate the first few KL terms and then try to somehow correct for the bias, but only at that level? And I don't have an answer to that question. So I will stop here. I will tell you that these Bayesian inverse problems are important computational problems, that multi-level methods can really help in increasing efficiency, both in a Markov chain setting and in an interacting particle setting. But I think the main issue that we have is what can we actually infer from the data instead of just computing high-dimensional posteriors and reporting them as being the most efficient way we can compute them. So I want to thank you for your attention.